Right. Thank you. Okay, now we take out the eigenvalues. L squared goes to L plus 1, h bar squared. H bar squared, L plus 1, L, and then this LZ squared goes to h bar squared, M squared. Minus h bar squared, because there's h bar here, M. And right? Oh, that's a normalization condition.
So you are in the state, so it's not necessarily normalized.
Correct. I want the state afterwards to be normalized, right? Okay. So let's figure out what this is. First of all, the h bar cancel because we have chosen so that everything remains dimensional. Okay. So on this side is L plus 1 L minus, we get M squared minus M. So let me turn this into L squared minus M squared. Okay. And then it's plus L minus M. Alright? So now this is just like the term we had before. We will have L minus M, L plus M plus 1. And immediately you see, well, this makes sense because we have that L minus M term here. Okay. And since this is the raising operator, if this was L, it would be 0, right? This CLL must be 0. And indeed, you see that here. So this must be correct. So now, other than a choice of the phase, because right now we have said the magnitude squared of CLM is equal to this, a real number. But CLM in general should be complex, because this might add a phase shift to it. So, but we're free to choose that phase. Okay. Now let's just choose it to be 1. Okay. So we get CLM is equal to the square root of L minus M, L plus M plus 1. Okay. So now the action of the L plus operator, the raising operator, is clear. So we get L plus L M is equal. Correct? So let's turn to the L minus operator, and we do exactly the same thing. So L minus L M, let's use some other notation, maybe D. Okay. DLM, this goes to L M minus 1. Okay. So now if you compute the bra of this, you get LM L plus. Right? And then I take the norm and require it to be normalized. Okay, and then on this side I will get DLM squared, magnitude squared. Okay. So we get DLM magnitude squared is equal to, where would be at h bar squared? LM okay, no problem. What is this? This just turns into, well, you get a h bar squared, obviously. So L plus 1 and minus M squared plus M. Right. So now we cancel the h bar squared. Okay. And we get the DLM. Right, there's a plus sign here, and before we had a minus sign, right? So the plus 1 will go with the L minus M. Right? So this is L plus M, L minus M plus 1. So the way you remember this is there's always a plus 1 because we're getting like difference of squares here. And then because for the raising operator, you would like when you operate on state LL, you get 0. Right? So it must be L minus M. But for the lowering operator, it must be L plus M because for minus L minus L, the raising operator destroys it. So that's how you should remember this. Okay. And these formulas are very easy to remember. Okay. Any questions so far? No?
You can like the first line of the blackboard, right, on the right, so you can get a phase to it. So
right,
can you explain how you get rid of the phase?
Just by convention, we choose it to be 1 because we're free to choose the phase here. And to make everything simple, we choose it to be 1. But the thing is, if you go from the route of solving explicitly the eigenvalue problems from the differential equation, and you use Legendre polynomials, the phase is actually, I think, -1. There turns out to be a difference. But from quantum mechanics, and everybody uses +1. Okay, so let's just use +1 for the phase. Yeah. Right. Okay.
Then what is D and M?
Also, D is it's just some arbitrary constant that we're going to find. Some arbitrary complex constant. Yeah. Okay. So if there are no problems, maybe we take a 5-minute break.
Okay.
Until 9:55.
The take-home exam 1 is great.
Right, you can get them after the class.
You can give them